Have you ever listened for the edge of home? Not a line on a map, but a fade, the solar wind thinning, the magnetic field loosening, charged particles changing their tune. That's where the Voyagers are now. Launched in 1977, with tape recorders and optimism, they threaded the giant planets and kept going, past the bow of the sun's influence into the interstellar medium. The signal is faint, the story clear, numbers that show where our system ends and everything else begins. Tonight we follow that trail, how the instruments work, what the readings mean, why the heliopause matters. If measured wonder is your thing, a like and subscribe helps more people find calm, curious science. Settle in. Beyond the stars isn't a slogan here. It's a set of coordinates. In the late 1,960 seconds and early 1,970 seconds, Earth lived with a steady tension that shaped choices in science as much as in politics. A period when the Cold War set two nations on parallel tracks, and the space race became one of the few arenas where rivalry could turn into discovery. The United States and the Soviet Union watched one another across oceans and ideas, building rockets not only to prove strength, but to reach beyond the atmosphere and learn what was really out there. In 1969, humans stepped onto the moon, and millions watched the broadcast in grainy black and white as Neil Armstrong and Buzz Aldrin moved across the surface. It was a clear, shared moment that capped the Apollo program and made the phrase, "We did it," feel true on a global scale. After that, public attention cooled. Repeating landings did not feel new. Budgets tightened. Missions ended before their time. NASA had to ask a practical question with real weight. After the tallest peak is climbed, where does the work go next? The answer waited beyond Mars. Among the giant planets that earlier programs could not reach, Jupiter, Saturn, Uranus, and Neptune, each a world of deep clouds, strong winds, complex rings, and unusual moons. They were large, cold, and distant, and for most people they existed as telescope blurs and textbook images, impressive but remote. Reaching even one of them demanded years of travel and careful planning. Reaching several in one flight seemed out of reach. Distance was the first barrier. These planets sit hundreds of millions to billions of miles away, far beyond the realm where a short cruise can deliver a spacecraft quickly. The idea of visiting all four in sequence sounded like a story device, not a plan you could debug in a lab. Then orbital timing opened a narrow door. Roughly every 175 years, the outer planets fall into a layout that allows a single probe to gain speed and change direction by dipping through a planet's gravity well, a method called a gravity assist. The spacecraft steals a tiny bit of the planet's orbital energy and aims for the next target. Engineers already knew the math, but the exact window beginning in the late 1,970 seconds made the path real. If a mission could launch on time, the probe could hop from one giant to the next, using physics to make up for what fuel could not supply. The concept was called the Grand Tour, an idea from the 1,960 seconds that imagined multiple probes visiting the outer planets and even Pluto, collecting images, fields, and particles along the way. It was bold and detailed and, under budget pressure, too costly. When Apollo wound down and new priorities arrived, the Grand Tour plan was set aside. The core of the idea survived in a simpler form. NASA chose to build two identical spacecraft and send them on slightly different tracks, aiming first for Jupiter and Saturn, with the possibility of reaching farther if systems held. This was Voyager. The design focused on reliability, smart use of power, and instruments that could return high-value data without heavy complexity. The expected lifetime on paper was about 5 years, long enough to reach the first 2 giants and complete the primary goals. Anything beyond that would be a bonus, not a promise. The technology of the 1,970 seconds set strict limits and forced careful choices. Computers on board were basic by modern standards and had to be programmed with great care. Memory was scarce, and every command sequence had to be tested repeatedly. Yet the design turned those limits into a strength by keeping systems modular and by using redundancy where it mattered. Power presented the next challenge. Solar panels drop in output with distance from the sun and become impractical in the cold outer reaches, so engineers chose radioisotope thermoelectric generators, or RTGs, compact power sources, that convert heat from the natural decay of plutonium into electricity. An RTG has no moving parts, works in deep cold, and can deliver steady power for decades, which is exactly what a far-traveling craft needs. Communication was another essential system. The farther a spacecraft travels, the weaker its signal becomes. So Voyager carried a large, high-gain antenna and depended on a network of big, Earth-based dishes, known as the Deep Space Network. Over time, the signal would sink below the level of ordinary background noise, but with long integrations, sensitive receivers, and carefully shaped waveforms, the data could still be pulled out and decoded. The instruments took measurements of magnetic fields, charged particles, plasma, and radiation, and the cameras and spectrometers captured images and spectra that could turn faint points into measurable worlds. There was also a human element that reached beyond engineering. A small team, led by Carl Sagan and colleagues, assembled a message meant for any intelligence that might someday find the spacecraft. The golden record, pressed in gold-plated copper, held music from many cultures, greetings in dozens of languages, natural sounds from Earth, and a set of images encoded as analog data, along with simple diagrams that explained how to play it. It even carried a record of human brain activity, a short snapshot of thought and feeling in electrical form. The record was not a claim that contact would happen. It was a careful statement about how humans chose to present themselves, living on a small planet around a yellow star, curious about the larger place we inhabit. Inside NASA's Jet Propulsion Laboratory, the work moved in steady steps. Teams validated components, checked every wire and fastener, tested each subsystem in thermal vacuum chambers, and built up flight software that could handle timed events and fault protection. The pace was not flashy, it was patient and exact. Stability mattered. The cameras had to focus and track across a huge range of brightness. The scan platform that aimed the instruments had to move smoothly at tiny angles. Thermal blankets had to hold temperature within a narrow band despite sunlight at Jupiter and deep cold beyond Saturn. Each change was logged, each test repeated until teams were sure. Scientists planned the flyby geometry to balance close looks at key targets with safety margins that reduced risk from radiation belts and dust. Image lists were built by hand, exposure times were calculated, and priorities were set, so the probes would not miss the high-value scenes: Jupiter's atmosphere, the Galilean moons, Saturn's rings, Titan's haze. Engineers worked on fault modes and recovery steps so the craft could handle glitches without losing the encounter timeline. The mission also required a ground system that could receive a trickle of data and turn it into useful results quickly. This meant coordinating between tracking stations, mission control, instrument teams, and image processing labs, all running on the best computers available at the time. The outer planets were still mostly unknowns. Neptune had no close-up images. Titan was a dim blur with a thick atmosphere. The edge of the solar system, the region where the sun's wind meets interstellar space, did not have a clear boundary in textbooks. Even so, the project moved forward with a straightforward belief that careful planning, clear math, and disciplined operations could extend our reach. The spacecraft carried more than instruments. They carried a record of how people solve problems when tools are limited and goals are long-term. The 1,970 seconds brought inflation, political debate, and shifts in public interest. Yet these two vehicles advanced with a design that valued durability and focus. The approach was simple: do the hard parts well, keep margins where they count, and accept that patience is part of the method. The mission profile set primary targets of Jupiter and Saturn for both craft. If performance held, one path could bend toward Uranus and Neptune, taking advantage of the rare alignment, while the other could study Saturn and its largest moon in greater depth. The fuel was mainly for attitude control and small trajectory corrections. The big changes would come from gravity assists. This meant timing mattered to the minute, and navigation teams refined trajectories with tracking data, small burns, and statistical filters that reduced uncertainty. The design of the instrument suite reflected a balanced view of what would matter up close and far away. Imaging would reveal weather systems, rings, and surface features. Spectrometers would identify gases and ices. Magnetometers would trace magnetic fields and show how they connect to moons and rings. Plasma instruments would map the solar wind and the way each planet shapes its local space. Together, they formed a toolkit that could turn first-time visits into durable knowledge, making the distant familiar without overselling what was not yet known. There was a quiet understanding that the spacecraft might keep working beyond the main tour. If that happened, the instruments that did not depend on sunlight could continue to collect data in the outer heliosphere, and, if the power and systems allowed, beyond the region dominated by the sun's wind. That possibility did not change the core plan, but it gave the teams a reason to design, with long life in mind, clean circuits, robust software, careful thermal control. As the launch window approached in 1977, assembly, test, and operations moved in a tight loop. Checklists grew precise. Commands were reviewed line by line. Image targets were arranged into sequences that the computers could run without human intervention during the fast hours around each flyby. The golden records went on last, bolted to the bus, labeled with simple instructions and a pulsar map that could point back to our place in the galaxy. The finish wasn't about show, it was about purpose. Two identical spacecraft, each with a focused set of instruments and a clear flight plan, were built to use a rare planetary alignment, reach the giant planets, map their fields and particles, return the data, and if power and hardware held, keep moving outward. That purpose shaped every design choice. Building for more than 40 years in deep space, with no repairs and no do-overs, meant picking reliability over flourish. In the early 1,970 seconds, the requirement sounded plain and demanding at once. Two robotic explorers that could travel billions of miles, study worlds no one had seen up close, and keep sending numbers back as they crossed from the sun's domain into the deep. Durability came first. Space is cold and harsh, filled with radiation, charged particles, and tiny bits of rock. Voyager's core used a stiff aluminum frame to survive, launch, and to hold instruments in alignment. Thermal blankets and coverings managed heat so parts stayed within working ranges. The aim was not to make a tank, but to protect what mattered while keeping mass low. The most visible feature was the high-gain antenna, a white dish about 3 meters across. It would focus a narrow radio beam toward Earth and listen for commands. Over time, the signal would fade to levels far below everyday noise. But the Deep Space Network, large radio dishes placed around the globe, could still pick it out and decode it. The antenna also shaded parts of the spacecraft, helping with temperature control. Inside sat modest computers by today's standards. Memory was measured in tens of kilobytes, so every bit had a job. Electronics were built to tolerate radiation and to run timed sequences. There were no live interfaces and no quick updates. As distance grew, commands took hours to arrive and status took hours to return, so the system had to be predictable and calm under delay. Power set the limits. Beyond Jupiter, sunlight becomes too weak for practical solar panels. Engineers chose radioisotope thermoelectric generators, or RTGs. These devices turn heat from the natural decay of plutonium-238 into electricity. Each spacecraft launched with 3 RTGs, producing roughly 470 watts in total, with output slowly decreasing over the years. Waste heat helped keep equipment warm. As power declined, the team turned off non-essential systems and scheduled instruments in turns. The instrument suite balanced discovery with weight and power. 10 main instruments flew: cameras, spectrometers, magnetometers, plasma detectors, and cosmic ray sensors. The imaging system adjusted exposure and filters for bright clouds and dark moons. A long boom held the magnetometers away from the body, so the spacecraft's own fields would not mask the signal. This spacing improved every magnetic measurement without adding complex shielding. Radiation near Jupiter drove careful layout. The giant planet's magnetic field traps charged particles and creates intense belts. Sensitive boards were placed inside protective housings and behind stronger panels. The goal was not invincibility, but survival for the crucial hours of each flyby. Trajectories were planned to reduce dose while keeping science value high. Because the mission used flybys, not landings, the design stayed lean. There were no legs, wheels, or parachutes, no sample collectors. The job was to approach, scan, and transmit. With that focus, engineers put effort into pointing accuracy, clean power, stable temperatures, and strong communications. Assembly took place in clean rooms where dust and moisture were tightly controlled. Every cable route, connector torque, and solder joint went through inspection and test. Orientation and navigation relied on gyroscopes and star trackers. The spacecraft compared star patterns to a catalog to know which way it was pointing. Small thrusters made tiny adjustments. During encounters, the scan platform swept instruments across targets, while operators balanced science time with the need to keep the dish aligned with Earth when possible. After a set of observations, the spacecraft reoriented to transmit data, then returned to science pointing. Dust and debris were part of the risk. Even a sand-sized grain can carry large energy at high speed. Voyager did not carry heavy armor, but vital components sat behind stronger panels, and encounter geometry avoided dust lanes and ring planes where possible. Risk was lowered by design, rather than eliminated by mass. Data moved in simple ways that worked at long range. Cameras sent images as streams of numbers, line by line. Spectrometers and particle instruments produced counts and voltages that became tables on the ground. Downlink rates dropped with distance, so image plans matched what the link could carry. Processing on Earth turned lines and counts into pictures and plots. The pace was slow by modern standards, but steady and reliable. Commanding depended on sequences. Teams wrote timed scripts that the spacecraft could run without real-time help during the busiest hours. Fault protection watched for signs such as low voltage, unexpected temperatures, or lost lock on the guide stars. If needed, the system entered a safe state that preserved power and pointed the antenna home. Controllers then analyzed the event, sent recovery commands, and resumed the plan. Thermal management was constant work. RTGs produced steady heat, radiators and blankets moved and held that heat where it helped. Components had preferred temperature ranges. Too cold and lubricants stiffen, too warm and lifetime shortens. Distance from the sun and pointing both changed temperature, so operations scheduled activities to keep parts within bounds. Calibrations gave data meaning. Before and after encounters, teams used known stars, internal lamps, and the deep space background to check instruments. Small drifts and biases were removed. Photometric tables turned pixel values into brightness and color. For fields and particles, calibration tied counts to physical units. These steps allowed comparisons across days, targets, and spacecraft. The long magnetometer boom created its own needs. It had to deploy cleanly and remain steady. Flexing could add noise to field data and smear images if motion coupled into the pointing system. Tests checked interactions between boom motion, scan platform motion, and attitude control. RTG supports also had to remain rigid across changing temperatures to avoid pointing errors. Software lived within tight limits. Code was compact and table-driven. Many adjustments were done by changing parameters instead of rewriting routines. Updates were uploaded in pieces and verified after each block. Reviews were strict because a single error could lock out science or communications for a critical window. Ground systems were as important as flight systems. The Deep Space Network scheduled passes and sometimes combined dishes to raise sensitivity. Navigation teams measured Doppler shifts and timing to refine the path. Imaging teams computed geometry so each pixel could land on a map. Planning groups set priorities when bandwidth and time were tight. Clear roles and documented procedures kept the machine and the people in sync. Instrument placement followed simple rules. Keep field sensors away from current loops. Keep optics away from warm surfaces and stray light. Keep cables short where timing matters, shielded where noise matters. When mass increased in one area, it decreased in another. Trade studies weighed grams against data return. The result was a compact layout with clean lines of function. Radiation hard parts were used where possible, and layout added more protection. Placing a sensitive board behind a tank or panel cut high-energy flux. Twisted pair cables and proper grounding reduced induced noise during strong field events. These choices lowered risk without adding much mass. As RTG power declined, careful power management kept the mission going. Heaters were removed from some zones. Instruments took turns. The transmitter ran at lower power when the link allowed. Small savings added up. Models tied power to temperature and duty cycle, and teams adjusted plans year by year. The camera system, though simple, delivered sharp results because exposure tables and pointing were prepared with care. Close-range scans used mosaics with overlap that could be stitched into global views. Longer-range frames gave context, showing where close-ups fit within larger cloud systems, rings, and terrains. Spectrometers identified gases and ices. Magnetometers traced field lines linking planets, moons, and rings, plasma instruments showed bow shocks and long magnetotails, and cosmic ray detectors tracked the slow change in particles with distance. Materials choices mattered. Lubricants had to work in vacuum and extreme cold. Coatings needed to resist ultraviolet light and radiation. Insulators had to avoid charge buildup that could discharge and harm electronics. These small choices in materials science added years of life. Testing made weak points visible on Earth instead of in flight. Thermal vacuum runs cycled temperature and pressure while instruments operated. Vibration tests simulated launch loads. Alignment checks confirmed that instruments pointed where the design said they would. After each test, teams inspected and adjusted. Documentation captured every change. Tools of the era, paper drawings, hand checks, punch cards, and mainframes shaped the process. What they lacked in speed, they made up in traceability. Designs had owners. Changes had reasons. Records showed how and why each decision was made. The same discipline carried into flight. As distance grew, round-trip light time stretched from hours to nearly a day, so operations shifted to a slower rhythm. Command plans were prepared in blocks, sent, confirmed, then reviewed against the data that came back. During close passes, timed onboard sequences carried the load, while the ground monitored margins and adjusted between segments. Two vehicles emerged from that methodical build, platforms able to hold attitude, sample fields and particles far from the sun, and talk across weak, long links with table-driven software that stays steady when contact is rare. By late summer 1977, they stood on separate pads in Florida atop tangent Centaur stacks, timed to a rare alignment fly past the giants, return what they recorded, and keep going as long as power and patience held. They were named Voyager 1 and Voyager 2. The numbering can be confusing at first glance. Voyager 2 launched first, on the 20th of August 1977. Voyager 1 followed on September 5. The numbers reflect arrival order, not launch order. Voyager 1's faster trajectory reached Jupiter and Saturn sooner, so it took the 1 designation. The idea behind sending two craft was simple. One would follow a quick route optimized for early returns at Jupiter and Saturn. The other would take a longer route that left the door open for Uranus and Neptune if the system stayed healthy. This split plan let the mission cover more ground without building new hardware. It also gave the team a second chance if one vehicle ran into trouble. The larger context mattered. About once every 175 years, the outer planets fall into positions that allow a single spacecraft to move from one to the next using gravity assists. A gravity assist is a guided fall and a fast exit. The probe approaches a planet, speeds up as it drops into the gravity well, whips around, and departs with a new direction and a higher speed relative to the Sunday. The planet loses a tiny bit of orbital energy, far too small to measure, while the spacecraft gains exactly what it needs. This trade turns long, fuel-hungry trips into a chain of doable steps. The alignment window in the late 1970 seconds gave engineers a rare path. If launch dates hit within tight windows, a single craft could visit Jupiter, then Saturn, and possibly Uranus and Neptune. Miss the window, and the sequence would shift out of reach for generations. That constraint shaped everything from the pad schedule to the smallest details of navigation. Voyager 2 went first because its route required more time to set up later encounters. It would aim for Jupiter and Saturn, and if possible, continue on. Voyager 1 followed a shorter, steeper arc to Jupiter and Saturn. After Saturn, its course would bend sharply out of the ecliptic plane, the thin disk where most planets orbit, sending it northward relative to the Sun's equator. This geometry set up two different kinds of exploration using the same toolkit. Both spacecraft rode Titan IIIe, Centaur launch vehicles. The rocket stack provided the push to escape Earth and the extra velocity to set the interplanetary path. Voyager 2's ascent included a brief data glitch from the upper stage that was quickly resolved. The trajectory stayed within plan. Voyager 1's ascent was smooth and precise. Within hours of each launch, ground controllers confirmed that both vehicles were healthy and on course. From the start, timing and navigation ruled the mission. Tiny errors at Jupiter would grow into big misses at Saturn. The navigation team used Doppler measurements, small changes in radio frequency caused by motion, and ranging signal travel time to refine the path. Mid-course maneuvers, short burns of the small thrusters trimmed velocity by fractions of a meter per second. These small changes moved in counterpoints by thousands of kilometers many months later, which is exactly what was needed to thread narrow aim points near the planets and their moons. Gravity assists were not just speed boosts, they were steering tools. At Jupiter, engineers could tune the flyby altitude and angle to set the arrival path at Saturn. At Saturn, a deeper or shallower pass set very different futures. A Titan encounter that bent Voyager 1 out of the plane, or a trajectory that let Voyager 2 continue outward. Each choice had to balance science, return, radiation exposure, and the health of the instruments. The math under the maneuver is straightforward in principle and careful in practice. Relative to the planet, the spacecraft falls in and climbs out with nearly the same speed. Relative to the Sun, the planet's motion adds vector components to the spacecraft's path. Set the aim point correctly, and the exit vector lines up with the next target. Aim slightly high or low, and the exit vector misses by millions of kilometers months later. The design team calculated these paths to fractions of a degree and seconds of timing. Every flyby doubled as a science campaign. Cameras, spectrometers, magnetometers, and particle detectors had jobs to do during short windows when detail was highest and lighting was right. Because radio signals took many hours to go one way, there could be no real-time steering during the busiest periods. Teams built long command sequences and loaded them before each encounter. The spacecraft executed the steps in order. Point the scan platform, take exposures, switch filters, sweep the field's instruments, and then re-aim the high-gain antenna to send data home. Voyager 1's quick path meant it would be the first to cross the boundary regions where the Sun's influence thins, but it would not continue to Uranus or Neptune. The price of a close Titan pass at Saturn was a sharp turn that sent the craft above the planetary plane. Voyager 2, traveling more slowly, kept to the plane and carried the mission onward to Uranus and Neptune, becoming the only spacecraft to visit those worlds up close. None of this was guaranteed when the rocket stood on the pads. The official commitment covered Jupiter and Saturn. Everything beyond was possible only if the hardware stayed healthy and if navigation hit the small targets. That is why the launch windows felt so strict. Missing a day could mean missing a geometry that set up the rest of the tour. The launches were steady and professional rather than dramatic. There were no crews on board, no live TV tours from the cockpit. The work took place in countdown rooms, in tracking stations, and at consoles where engineers watched numbers roll and stayed ready to correct when a value drifted out of range. The first hours confirmed power, temperatures, attitude control, and link quality. The first days checked instrument health and calibration lamps. Then came months of cruise, small corrections, and regular status checks. As each spacecraft settled into its path, the team refined encounter plans. For Jupiter, radiation belts required careful timing and shielding strategies. For Saturn, the priorities included ring structure, the atmosphere, and the haze of Titan. The geometry of each pass set the pace and the workload. The faster the pass, the shorter the time for high-resolution imaging, and the more precise the pointing had to be. Gravity assists gave the mission a rhythm: approach, accelerate, turn, and depart with a new speed. The numbers tell the story. A few kilometers per second gained at Jupiter set up the timing at Saturn. The Saturn turn for Voyager 1 changed its inclination by dozens of degrees. The gentler Saturn pass for Voyager 2 preserved a path along the ecliptic that intersected Uranus years later and Neptune years after that. Each bend came from mass and motion, not from extra fuel. The operations model respected light time delay. A command sent to a spacecraft many astronomical units away would arrive hours later. A reply would take the same time to return. This forced careful sequencing and clear fallback plans. Safe mode logic would point the antenna at Earth and wait for instructions if something unexpected happened. Controllers then analyzed telemetry, built a recovery plan, and resumed the timeline without rushing steps that could cause more harm. The launch vehicles did their job, but the long mission depended on small adjustments made well after liftoff. Tracking stations measured frequency and time with high precision. Software fit the data to trajectory models and produced burn plans that used very small propellant amounts. Each burn was verified by post-maneuver tracking, and the next plan was updated with the new state. Instrument teams treated each encounter as a once-only chance. Exposure tables accounted for changing light. Scan patterns covered cloud bands, ring gaps, and moon surfaces with overlap for later mosaics. Fields and particles teams set sweeps that would map bow shocks and magnetotails, while magnetometer teams tuned ranges to avoid saturation near strong fields and preserve sensitivity farther out. Months of planning condensed into hours of execution. The split paths after Saturn followed from earlier choices. Voyager 1 took the Titan option and turned north of the planetary plane. Voyager 2 stayed in the plane for Uranus and Neptune. These were not story beats. They were route settings that used the best information available at the time. The mission design kept flexibility where possible and locked in decisions when the physics of timing required it. What defined this phase was alignment and patience. A rare geometry made the tour possible, and the launch sequence honored that geometry. Navigation kept each spacecraft inside narrow flight corridors where gravity would do most of the work, and the science plan fit inside those lanes without forcing changes that could break the path. As the first weeks passed, both Voyagers settled onto their interplanetary tracks. Hardware stayed stable, the radio links were clean, and the clock to first encounter mattered more than the memory of launch. Small trajectory corrections trimmed the aim points. Command sequences shifted from paper timelines to calendars set by orbital mechanics and light time. Jupiter then grew from a bright disk into a world with fast weather and a strong radiation environment. For decades, it had been striped and distant, impressive, but vague. The flybys changed that. Voyager 1 reached closest approach on the 5th of March, 1979. About 349,000 kilometers is approximately equal to 217,000 miles above the cloud tops. Voyager 2 followed on the 9th of July, 1979, along a similar path. Those passes turned a blur into a measured system, with features, motions, and fields that could be mapped and compared. The atmosphere showed bands at every scale. From far away, the belts and zones looked smooth. Up close, they broke into cells, eddies, and long jet streams that moved in opposite directions. Bright storms appeared as ovals with sharp edges. Dark lanes marked regions where air sank and cleared the haze. The Great Red Spot stood out as a stable, high-pressure storm rotating counterclockwise in the southern hemisphere. Voyager's images resolved filaments and smaller swirls wrapping around its core. The winds there moved faster than the strongest hurricanes on Earth, and the storm covered an area larger than our planet. Nearby, other ovals and spots formed, merged, and faded on timescales of days to months, showing that the atmosphere is a layered, moving fluid rather than a single, uniform shell. Jupiter's size and spin set the stage for this motion. The planet is about 11 Earth diameters wide and more than 300 Earth masses. A day on Jupiter lasts under 10 hours because of rapid rotation. That rotation stretches the atmosphere into belts and zones through a process called differential rotation, where different latitudes move at different speeds. The main gases are hydrogen and helium. Clouds form from ammonia, ice, and other compounds at different pressures and temperatures. With depth, pressure rises until the hydrogen behaves like a fluid. The energy sources driving the weather include sunlight and internal heat left from formation. The combination feeds long-lived storms and fast jets. The moons change the picture even more. Before the flybys, astronomers expected cold, cratered bodies with few surprises. Voyager showed 4 large satellites: Io, Europa, Ganymede, and Callisto, each with its own kind of activity and history. Io became the first world beyond Earth where active volcanoes were seen. Cameras recorded plumes shooting hundreds of kilometers above the surface. The ground appeared in sulfur-rich colors with fresh flows and caldera-like pits. The cause is tidal heating. Io moves in an orbit that is slightly stretched by Jupiter's gravity and by resonances with Europa and Ganymede. As the moon flexes, friction inside it generates heat that melts rock. That heat feeds constant eruptions and renews the surface on short timescales. Europa presented a smoother face. Few craters and long, dark lines crossed a bright, icy crust. The lines are fractures where blocks of ice moved and refroze. The surface pattern suggested that the ice shell floats on a global ocean of liquid water kept from freezing solid by tidal heating. The ocean would be under many kilometers of ice and likely salty. That simple set of clues, young ice, fractures, and the right energy source placed Europa high on the list of possible habitats for life, not because life was detected, but because liquid water plus energy is a basic requirement for many forms of life as we know it. Ganymede turned out to be the largest moon in the solar system, bigger than the planet Mercury. Voyager images showed older, darker areas, cut by bands of lighter, grooved terrain. Those grooves are long ridges and troughs that mark past tectonic activity in the ice-rich crust. Later missions confirmed that Ganymede has a magnetic field of its own, but even with Voyager's early data, it was clear that the moon had a complex interior and a history of internal change. Callisto looked older and quieter. Its surface was heavily cratered, with bright rings around large impact sites and fewer signs of internal reshaping. The contrast between Ganymede and Callisto showed that even similar-sized icy worlds can follow very different paths depending on heat sources and internal composition. Closer to Jupiter, small inner moons contributed to another discovery: rings. Voyager detected faint rings made of dark, dust-sized particles extending around the planet. The material likely comes from micrometeorite impacts on small moons, which kick up debris that spreads into thin bands. These rings are not bright like Saturn's. They are hard to see in visible light, but they revealed that ring systems can form wherever small particles are supplied and confined by gravity. Jupiter's magnetic environment was intense. The planet's fast rotation and conducting interior generate a strong magnetic field that shapes a huge region of space called the magnetosphere. In that region, charged particles spiral along field lines, forming belts of radiation that can damage electronics. Voyager carried shielding and planned quick passes through the harshest zones. Measurements mapped the field's strength and direction and counted particles. The data showed bow shocks where the solar wind slowed and diverted around the magnetosphere, and long magnetotails stretching away from the Sunday. The interaction between the field and the moons created additional effects. Io's volcanism supplies neutral gas that becomes ionized and trapped, forming a plasma torus along Io's orbit. That plasma feeds currents that connect Io to Jupiter's poles and help power bright auroras. Auroras at Jupiter's poles were bright in ultraviolet and variable in shape. They formed where energetic particles followed magnetic field lines into the upper atmosphere and collided with gases, causing them to glow. The patterns differed from Earth's because of Jupiter's stronger field, fast spin, and the supply of particles from its moons. The result was a set of lights that changed with the planet's rotation and with the state of the plasma environment. The imaging sequence at Jupiter required careful timing. The scan platform moved the cameras and spectrometers across targets to build mosaics. Exposure times had to balance motion blur against faint detail. Filters isolated specific colors to identify cloud layers and hazes. Close-ups of the red spot and nearby ovals documented shear zones and small vortices feeding into the main circulation. LIM images, views of the edge of the planet, showed vertical structure in the haze layers. Time-lapse sequences tracked how features moved, giving wind speeds at different latitudes. Io's volcanoes were confirmed through a mix of imaging and careful comparisons. Plumes appeared as umbrella-shaped hazes rising above the limb. On the days between Voyager 1 and Voyager 2 passes, some features changed, revealing new flows and darkened areas. That pace of change could not come from slow processes like space weathering. It had to be ongoing activity. The identification of volcanic gases matched the colored deposits seen on the ground, tying chemistry to geology. Europa's fractures formed long, intersecting networks. Some lines look like double ridges with a central trough, a shape consistent with ice cracking, opening slightly and then freezing again. Where ridges cross, patterns indicate repeated motion rather than a single event. Smooth plains suggest resurfacing over large areas. Without many craters, the surface must be young in geologic terms. The simplest way to replace old, cratered ice with young, smooth ice is to have a mobile layer below it that can supply new material. Ganymede's grooved terrain cut across older, dark regions and kept a consistent orientation over long distances, evidence of stress fields in the crust over time. Callisto's bright ring structures around large craters, such as the multi-ring basin Valhalla, implied a layered, brittle surface that responded to big impacts in predictable ways. These observations gave a first-order classification. Io, active and hot. Europa, icy with signs of a subsurface ocean. Ganymede, tectonically reshaped. Callisto, ancient and stable at the surface. Particle instruments recorded how the environment changed near each moon and across the magnetosphere. Dips and spikes in counts marked boundaries between regions. Magnetometer readings traced field lines bent by currents. Plasma wave instruments picked up radio emissions tied to auroral processes, and to interactions with Io's plasma torus. Together, these datasets described a system where a giant planet, a strong magnetic field, and multiple active moons interact in ways not seen around Earth. The faint rings required special viewing angles, backlit geometries where the sun sat behind the planet relative to the spacecraft, made small dust particles scatter light forward and become visible. Images taken in that geometry revealed the main ring and a halo-like component, plus a tenuous gossamer ring associated with small inner moons. The discovery expanded the idea of what counts as a ring system and how fragile and dynamic such systems can be. Operations during the flybys followed a strict plan. The high-gain antenna pointed at Earth when possible to send back data. During the fastest parts of the encounter, storage and timing limits meant some data would be recorded and sent later. After the closest approach, the sequence shifted to long-range monitoring to catch changes and to tie close-ups to their larger context. Each step was designed to maximize return while protecting the spacecraft in high radiation zones. The raw images arrived as streams of numbers that became grayscale frames. Ground processing, set contrast, mosaiced overlapping shots into global views, and combined filter sets to make color composites both approximate true color and false color maps that tease out composition and cloud height. With limited bandwidth, targeting mattered. Sequences were timed to catch limb views for vertical structure, high phase angles for hazes and rings, and time-lapse runs for wind speeds. From those choices came a coherent picture at Jupiter fast, zonal winds, long-lived vortices, a strong magnetic field, bright auroras, a ring so faint it needed backlighting, a plasma torus tied to Io's volcanism, and moons that both respond to and reshape their environment. The result was a working model of a gas giant from cloud tops to the edge of its magnetic reach. That same method carried forward to Saturn. The planet first resolved as a pale, banded globe with a wide, flat ring system once misread as ears in early telescopes, later known as sheets of ice and dust. Voyager 1 flew by in November 1980 at about 124,000 kilometers, 77,000 miles, above the clouds. Voyager 2 followed in August 1981, a bit closer. The paired encounters replaced textbook art with measurements, high-resolution imaging, and spectra for clouds and rings, magnetometers for field strength and tilt, plasma and particle detectors for radiation belts and ring-moon interactions. Together, they defined the system in detail and set the baselines that later missions would refine. The rings dominated first impressions. They extend more than 270,000 kilometers, about 170,000 miles, in diameter, yet are extremely thin, typically tens of meters thick. Voyager's cameras showed that what had looked like broad bands from Earth was actually a fine structure of thousands of ringlets. Gaps appeared at many scales. The Cassini division, long known as a dark lane between the A and B rings, contained its own narrow rings when viewed up close. Voyager also resolved the Encke gap inside the A ring, a clear, sharp corridor maintained by gravitational dynamics. Small moons near the ring edges, shepherd moons, helped keep boundaries crisp by nudging particles back into place with repeated, gentle pulls. Patterns crossed the rings that did not fit simple orbital spacing. Waves and bending features traced resonances with interior moons. Radial spokes appeared as grayish streaks sliding across the B ring. Their contrast changed with lighting and Saturn's rotation, suggesting fine dust temporarily lifted above the ring plane, likely by electric charging in a magnetic environment. the spokes were transient. They formed, faded, and reformed over hours to days, evidence that the rings are an active disk rather than a static plate. Composition measurements pointed to water ice as the main ingredient, mixed with darker material. Particle sizes ranged from dust to boulder scale. The brightness and color changed with viewing angle, a sign of how small grains scatter light. Backlit geometries made the thinnest components stand out, while forward scattered light traced faint sheets that are invisible in other views. Together, these effects mapped where particles of different sizes dominate and how collisions and resonances sort them. Saturn's atmosphere looked calmer than Jupiter's, but showed steady motion. Broad belts and zones wrapped around the planet, driven by rapid rotation. A Saturn day lasts roughly 10.5 hours. Voyager tracked jet streams at multiple latitudes and watched storms that rose and decayed over weeks. Cloud tops consist mainly of ammonia ice, with deeper layers of ammonium hydrosulfide and water forming at greater pressures. Temperature profiles and wind speeds derived from image sequences and spectra built a vertical picture of the weather. Near the poles, Voyager recorded wave-like features that hinted at unusual circulation. The polygonal hexagon at the North Pole would be mapped in detail by later missions, but Voyager's data already showed that Saturn's polar dynamics differ from simple banded flow. Saturn's magnetic field and radiation environment formed another layer of the system. The field, generated by currents in a conducting interior, carved a magnetosphere around the planet. Charged particles spiraled along its lines and formed radiation belts less intense than Jupiter's, but still important for spacecraft safety. Voyager's magnetometers traced the field strength and tilt. Particle detectors measured how populations changed with distance and local time. Radio and plasma wave instruments picked up emissions tied to auroras and to interactions between the field, the solar wind, and orbiting bodies. Titan stood out among the moons. It is larger than Mercury and holds a dense atmosphere. Voyager's instruments measured a surface pressure higher than Earth's and a composition dominated by nitrogen with methane and other hydrocarbons as minor components. Thick orange haze blocked optical views of the surface, so cameras saw only the top of the atmosphere. Even so, the data established that Titan is the only moon with a substantial atmosphere and the chemistry to build complex organics. To obtain those measurements and refine the atmosphere profile, Voyager 1 aimed for a close Titan flyby. That aim point bent its path steeply out of the planet's orbital plane and ended its chance to reach Uranus and Neptune. The choice was deliberate. One spacecraft prioritized Titan, the other kept the alignment for the outer tour. Voyager 2 skipped the Titan close-up and stayed in the ecliptic plane, keeping a route toward Uranus and Neptune. Before leaving Saturn, it surveyed many smaller moons. Mimas showed a dominant impact basin that covers much of one hemisphere. Tethys and Ione displayed bright terrain cut by canyons and fractures in ice-rich crusts. Rhea showed a heavily cratered surface. Enceladus appeared unusually bright, with smooth, young areas mixed with older, cratered plains, clues to internal activity that later missions would confirm as ongoing. These surfaces recorded differing heat histories. Some moons cooled and kept old craters. Others were resurfaced by tectonics or cryovolcanic processes that moved and refroze ice. The ring-moon connection was visible in several ways. Small moons embedded near gaps acted as shepherds that kept edges sharp. Resonances between moons and ring particles launched density waves, repeating ripples whose spacing and amplitude matched the math of orbital forcing. Faint ring components extended outward, aligned with the orbits of tiny, hard-to-see satellites that likely supply fresh dust after micrometeorite impacts. The system looked organized by gravity and collisions into a layered, evolving structure. Imaging at Saturn required precise planning. The scan platform pointed cameras and spectrometers along pre-computed paths to build mosaics across rings, cloud belts, and moon surfaces. Exposure times balanced motion blur against sensitivity. Filters isolated wavelengths that sampled different cloud layers and ices. LIM views the edge of the planet, and rings explored vertical thickness and hazes. Sequences over hours tracked wind speeds and wave growth. The geometry of each pass set the timing: fast, near closest approach; slower, far away, with data stored and sent as downlink allowed. Fields and particles measurements ran continuously through the encounters. Magnetometers recorded vector fields as the spacecraft crossed current sheets and lobes. Plasma instruments mapped boundaries where the solar wind met the magnetosphere and where ring ionospheres added local structure. Charged dust detectors counted small grains tied to ring processes. Radio occultations, in which the spacecraft's signal passed behind the rings or atmosphere as seen from Earth, gave density and temperature profiles with kilometer-scale resolution. The variety among the mid-sized moons reflected differences in composition and internal heat. Ice behaves as rock at Saturn's temperatures, but it can still flow slowly or fracture when stresses build. Bright, fresh ice marks recent exposure, while darker tones suggest older surfaces, mixed with meteoritic dust. Grooves, scarps, and smooth plains hinted at episodes when interiors were warm enough to allow movement. Impact features recorded the flux of debris over time and the mechanical strength of icy crusts. Saturn's gravity field and the distribution of mass in the rings and moons left signatures in tracking data. Tiny shifts in spacecraft velocity during close passes constrained the density of ring regions and the masses of small satellites. These numbers tied dynamical models to observed structures. In the rings, areas with more mass damped wave amplitudes. Areas with less mass allowed larger excursions. At moon flybys, gravity assists slightly altered the spacecraft paths while revealing the moon's internal heft. Voyager's observations established that the rings exchange material with moons and with the magnetosphere. Ultraviolet data sensed water vapor and hinted at sputtering processes, molecules knocked off icy grains by radiation. The balance between supply, impacts, erosion of small moons, and loss, drag, sputtering, spreading, determines ring lifetime. The detailed structure, from sharp edges to wavy gaps, comes from ongoing resonances and continual, gentle collisions among particles. Titan's hazy profile was measured with multiple techniques. Occultations of starlight and of the spacecraft's radio signal traced how pressure and temperature changed with height. Photochemical models matched the presence of complex hydrocarbons formed when sunlight and energetic particles break apart methane and nitrogen and rebuild them into heavier molecules. The result is a high atmosphere filled with small haze particles that settle slowly downward. These findings set later mission goals to peer through the haze with radar and infrared instruments. Across the system, timing and geometry determined what could be seen. Ring spokes were most apparent at certain phase angles. Storm contrast improved in specific filters. Moon surfaces revealed composition through absorption bands in ice. The mission used every favorable angle that the brief encounters allowed, then filled gaps with context imaging on the outbound legs. Data rates dropped with distance, so planning emphasized targets that answered core questions about dynamics, composition, and interactions. The Saturn phase showed a planet with fast rotation, a layered atmosphere, and a strong magnetic field. A ring system shaped by gravity, collisions, and electric effects, and a diverse set of icy moons with distinct thermal and mechanical histories. The close passes produced calibrated images and measurements that set baselines for later missions and gave clear reference points for how a ringed giant and its satellites behave under the same physics that operate throughout the outer solar system. By the mid-1980 seconds, Voyager 2 had already flown past Jupiter and Saturn with a solid set of results. The same design, the same careful planning, and the same patient operations now aimed at two colder, dimmer targets, Uranus and Neptune. No spacecraft had visited them. The alignment that made the route possible would not return for generations, so the team kept the hardware healthy and the navigation tight. Uranus came first. Voyager 2 reached closest approach on the 24th of January 1986, passing about 81,500 kilometers, 50,600 miles, from the cloud tops. From Earth, Uranus usually looks like a quiet blue-green disk. Up close, the planet kept that calm look in visible light, but instruments picked out wind, thin cloud bands, and temperature patterns that a small telescope cannot show. The planet's tilt stood out as the key oddity. Uranus spins on its side with an axial tilt near 98 degrees. That means one pole can face the sun for more than 20 years while the other stays in shadow. Then the situation flips. During the flyby, the south polar region faced the sun, so the view saw one hemisphere well and the other at a steep angle. Seasons on Uranus are long and extreme by design. Temperatures ran cold, near 59 kelvins, about 371 degrees Fahrenheit, at the cloud tops. The main gases are hydrogen and helium, with a bit of methane, which absorbs red light and gives the planet its color. Image sequences tracked winds that reached hundreds of miles per hour, but the contrast was low, so the motion showed up best when images were processed to bring out subtle changes. Even without big storms, the data proved that Uranus has active weather, driven by sunlight, internal heat, and fast rotation. The magnetic field added another layer of difference. Earth's magnetic dipole points roughly along the rotation axis. Uranus does not follow that rule. Its magnetic field tilts by almost 60 degrees relative to the spin axis, and the center of the dipole is offset from the planet's center. The result is a magnetosphere that shifts shape as the planet turns, with field lines and particle regions moving in and out of the solar wind in a way that varies over a single Uranian day. Voyager's magnetometer traced these changes, while plasma and wave instruments measured the charged particles trapped by the field. The rings around Uranus looked faint and narrow. They were first detected from Earth in the late 1970 seconds. Voyager confirmed 9 main rings and filled in details. Dark material, sharp edges, and gaps held in place by small moons and resonances. The particles reflect little light, which is why the rings are hard to see. Their thinness and darkness suggest a steady balance between supply from micrometeoroid impacts and loss by spreading and erosion. Uranus's moons gave the strongest surprises. Voyager 2 discovered 10 new small moons and mapped the 5 larger ones: Miranda, Ariel, Umbriel, Titania, and Oberon in much higher detail than before. Miranda stood out. Its surface looked like a set of mismatched pieces pressed together, bright and dark patches, ridges and troughs, and scarps that drop for up to about 20 kilometers, 12 miles. The cliff called Verona Rubes is among the tallest known in the solar system. Several ideas can explain that terrain: partial breakup and reassembly after big impacts, or strong internal stress that lifted and faulted an ice-rich crust. The images do not lock in a single history, but they show that even a small moon can record violent change. Aerial showed bright, youthful surfaces with long canyons and smooth plains, signs that ice once flowed or was resurfaced by internal activity. Umbriel appeared darker and older, with more craters and less evidence of reworking. Titania and Oberon, the largest two, mixed ancient cratered terrain with troughs and faults that hint at past tectonics. The range across these 5 bodies showed how size, composition, and heating shape icy worlds over time. From Uranus, the trajectory set a long cruise to Neptune. Voyager 2 covered the final billions of kilometers over 3.5 years, making small course corrections based on Doppler and ranging data. The closest pass at Neptune came on the 25th of August, 1989, at roughly 4,950 kilometers, 3,080 miles above the cloud tops. If Uranus looked understated, Neptune looked active. The same methane gives a deeper blue tone, but the atmosphere carried higher contrast features during the season of the flyby. The images showed the Great Dark Spot, an oval storm about the size of Earth, with bright companion clouds made of methane ice. Wind measurements reached up to about 2,100 kilometers per hour, 1,300 miles per hour, the fastest sustained winds recorded on any planet. How a distant, cold planet supports such strong winds is still a physics question. Likely sources include internal heat flow and the way stable layers in the atmosphere allowed jets to form and persist with little friction. Neptune's magnetic field mirrored Uranus in its odd geometry, tilted far from the spin axis and offset from the center. The magnetosphere responded to rotation with large changes every Neptunian day. Radio and plasma measurements tracked these swings and recorded emissions connected to auroral processes and to interactions between the field and the solar wind. The data fit a picture where a conducting layer deep inside, probably water ammonia fluid at high pressure, drives a dynamo that is not centered the way Earth's iron core dynamo is. Neptune also has rings. They are faint and dusty, with prominent arcs, clumpy segments that are brighter than the rest. Voyager 2 confirmed these arcs and mapped their positions. The arcs likely persist because of gravitational effects from small nearby moons that confine the material. The rings add to the pattern seen at Uranus: dim, narrow structures maintained by resonances and a steady exchange of particles. Triton, Neptune's largest moon, became one of the most interesting targets of the entire mission. It orbits in a retrograde direction opposite Neptune's rotation, which points to capture rather than formation in place. The surface temperature is extremely low, near 38 kelvins, about 391 degrees Fahrenheit. Despite the cold, Voyager 2 saw active geysers, thin jets of nitrogen gas rising several kilometers above the surface, leaving dark streaks where the wind carried particles downrange. This kind of cryovolcanism, volcanic activity driven by volatile ices rather than molten rock, implies internal energy. Tidal heating from a past orbit change or the decay of radioactive elements could supply that energy. Triton's surface showed smooth plains, ridges, and patterns sometimes called cantaloupe terrain, a set of rounded depressions and mounds that do not match common crater fields. The thin nitrogen atmosphere produced a light haze and supported weak winds that shaped the plume streaks. Together, these signs pointed to an active world, one that had been modified long after its formation and might still be evolving slowly. Alongside Triton, Voyager 2 discovered 6 new small moons and characterized others already known. Close passes and tracking allowed estimates of masses and densities. Those numbers, combined with images, placed the moons on a spectrum from dark, likely carbon-rich bodies to brighter, ice-dominated ones. The system as a whole fit the pattern seen at other giants: rings supplied by small moons, and small moons shaped by impacts and slow surface processing. Operations at both ice giants followed the model refined at Jupiter and Saturn. The scan platform moved through pre-planned sequences to build mosaics and to catch targets at the right phase angles for composition and haze studies. Occultations of stars and of the spacecraft's radio signal measured temperature and density profiles in atmospheres and rings. Magnetometer booms, plasma detectors, and wave instruments ran continuously to map the fields and particle environments before, during, and after closest approach. Data rates were low at those distances, so the plan balanced close-up imaging during the fastest hours with broader coverage on the way in and out. The 2 flybys added a class to the planetary catalogue. Uranus and Neptune shared traits similar sizes, similar bulk compositions, with a large fraction of ices, water, ammonia, methane, in high-pressure forms, and unusual magnetic fields. Yet their atmospheres, ring systems, and moons differ in important ways. One looked muted in visible light during the season of the flyby. The other showed high-contrast storms and very fast winds. One set of moons emphasized fractures and odd terrains on small bodies. The other featured a captured world with active geysers and a thin air. Numbers anchored the pictures. Dates of closest approach fixed the geometry. Distances set the scale of features. Wind speeds, temperatures, and field orientations turned images into physics. The discoveries depended on navigation that hit narrow aim points months after small thruster burns, on instruments that stayed calibrated after more than a decade in space, and on ground systems that could pull signals out of noise at the edge of the network's reach. After Neptune, the route no longer offered new planets. The instruments that do not need much power continued to sample fields and particles as the spacecraft moved outward. The cameras finished their main work. Other sensors carried on. The records from Uranus and Neptune stood complete. 2 distant planets observed up close for the first time, with rings, winds, tilted fields, and moons that showed active histories. Long before streaming or viral clips, 2 spacecraft carried a physical message from Earth. Each Voyager holds a golden record, an analog 12-inch gold-plated copper disc sealed in an aluminum cover, with a stylus and simple instructions etched on the outside. The concept came from a small team led by astronomer Carl Sagan. The Voyagers were already set to survey the outer planets and then continue outward. If they were likely to leave the solar system, the team reasoned, they could also carry a compact sample of life and culture. The chance of discovery by another civilization was tiny, but the task was clear: build a durable, readable record that explains itself. Time was short. The team had only months to choose content and manufacture the discs before launch. They treated the record as a time capsule and a technical artifact rather than a broadcast. The cover uses basic physics to bridge language gaps. Diagrams of the hydrogen spin-flip transition as a time unit, a map of 14 pulsars with their periods to mark our location, and instructions showing how to place the needle, set the speed, and decode images from the recorded signals. A cartridge and stylus ride with the disc so a finder would not need to invent a compatible tool. Spoken greetings open the audio. There are messages in 55 languages, from Akkadian, an ancient Mesopotamian language, to modern tongues including English, Mandarin, and Arabic. Some greetings are formal, others casual. One English line is, "Hello from the children of planet Earth," spoken by a child. Short and direct, it sets the tone for the rest. Simple statements that do not assume shared culture. Natural sounds follow to build a sensory map of the planet. The sequence includes wind and surf, rain and thunder, birds and insects, a heartbeat, a kiss, laughter, and a Saturn V rocket at liftoff. The humpback whale song is part of the set, chosen because its long, structured phrases show pattern in a non-human voice. These sounds are not random effects. They sketch air, water, weather, animals, and technology, everyday physics, as heard from ground level. Music takes the largest share of the audio. The selections aim for range over fashion. Western classical pieces include a movement from Bach's Brandenburg concertos. Traditional music appears from many regions: Indonesian gamelan, a Navajo night chant, Japanese shakuhachi, and a Peruvian wedding song. Blues is represented by Louis Armstrong's Melancholy Blues and by Blind Willie Johnson's Dark Was the Night, Cold Was the Ground, a wordless slide guitar performance whose tone carries emotion without translation. Popular catalog limits existed. For example, the Beatles' Here Comes the Sun was proposed but not included because of rights issues. The final program is about 90 minutes of audio, cut and mastered to a consistent level, and pressed in a durable analog format that tolerates age and minor damage better than early digital media. Images are recorded as analog signals that can be reconstructed by following the cover's decoding key. There are 116 pictures, landscapes from deserts, forests, mountains, and oceans, animals and plants, diagrams of DNA, cell division, human anatomy, and units, scenes of daily life such as eating, farming, building, and learning, tools and transport, and an image of Earth seen from space. Several frames give scientific reference points, mathematics, spectra, and measurements so a reader can calibrate, scale, and brightness. The collection avoids text. Labels are replaced by context and by repeated motifs so that a careful viewer can infer relationships among images. A short technical section in the audio explains how to read the images from the grooves, using a tone that acts as a line clock. The goal is minimal ambiguity. If a finder understands frequency, time, and ratio, the decoding is possible. The cover's pulsar map fixes the record's origin in both space and time, since pulsar periods slow at known rates. The hydrogen transition used as a base unit is common to matter across the galaxy, making it a practical clock. One track is more personal, an hour of brainwave and heart data from Anne Druyan, a member of the production team. Electrodes recorded her signals while she thought about basic ideas, history, people, and emotions. The recording does not claim to play back thoughts. It is a physiological trace. Its inclusion shows that biology can be presented as data, just as language and music can be presented as sound. The record also includes a printed key for unit conversion. Pictures show a human with a height scale, the solar system, and the trajectory of the Voyager spacecraft out of the ecliptic. The idea is to offer multiple anchors. If one method of interpretation fails, another might succeed. Redundancy appears in audio too. For instance, the sequence of natural sounds and music repeats concepts of rhythm and pitch in different styles, which could help a listener confirm playback speed and equalization. Durability was part of the design. Gold plating resists corrosion. The aluminum cover shields against dust and micrometeoroids. The stylus and cartridge are fixed to the case with a diagram to reduce guesswork. The analog format can be recovered without knowing any human codec. A needle and a consistent spin rate are enough to produce a signal that can be analyzed with basic tools. 2 copies of the golden record were built and mounted on the Voyagers with their covers facing outward. The mounting position reduces the chance of abrasion from dust along the flight direction. The discs are not transmitters. They are passive objects that require an encounter. The Voyagers travel fast on interstellar scales, but space is large and sparse. The team knew the probability of recovery was extremely low. The value, from their point of view, came from making a clear, honest sample of Earth at a specific moment and sending it on a path that leaves the Sun's neighborhood. The content choices have limits. 90 minutes is not enough to represent every region or tradition. The image set leaves out many people and places. The audio cannot capture scent, taste, or touch. Still, the project uses breadth over depth to suggest variety. Multiple continents, multiple eras, multiple technologies. The point is not to define Earth, but to provide enough signals that a patient reader can infer a living world with water, weather, many species, tool use, and abstract thought. Engineering tied the record to the mission. The added mass was small. The geometry of the cover let engineers etch instructions without weakening the case. The record survives the temperature swings of cruise. It does not need power from the spacecraft. Once attached, it became a stable part of the vehicle's outer structure. The golden record rides with instruments and hardware built for science, not ceremony. As the Voyagers crossed the orbits of the giant planets and moved outward, the discs remained unchanged. They are not part of flight operations or data return. Their role is to exist, readable by any toolmaker who finds them. 2 identical artifacts now travel on different paths, each marked by the same units and maps, each carrying the same audio and images, each prepared to be understood by someone who begins with physics and patience. When Voyager 1 and Voyager 2 lifted off in 1977, our view of the outer solar system was broad and blurry. We had a few close images from earlier probes, many telescope observations, and models that filled the gaps. The giant planets were far, dim, and hard to read. The twin spacecraft changed that. They did not just add sharper pictures. They replaced guesses with measurements and turned vague ideas into working explanations. The clearest shift came from the moons. Many were assumed to be cold, cratered bodies with little to say. Close passes showed active, diverse worlds. Io, circling Jupiter, became the first confirmed case of ongoing volcanism beyond Earth. Voyager 1 recorded tall plumes rising above the limb and fresh flows spread across a surface rich in sulfur compounds. The driving force was tidal heating. Jupiter's gravity and resonances with nearby moons flexed Io enough to melt rock. The result was rapid resurfacing and a landscape that changed on human timescales. Europa looked quiet from a distance. Up close, it held long, dark fractures and fresh, bright plains. The simplest red was a thick shell of ice floating on a global ocean warmed by tidal energy. The surface showed few craters, so it had to be geologically young. Those signs, combined with a steady energy source and the chemistry of ice and salts, placed Europa among the best candidates for subsurface water and possible habitability. Around Saturn, Enceladus appeared unusually bright, with smooth regions mixed with older, cratered ground. The lack of heavy cratering hinted at resurfacing. Later missions would find active plumes, but Voyager set the stage by mapping the youthful terrains. Titan, larger than Mercury, carried a thick nitrogen atmosphere with methane and complex hydrocarbons. Cameras could not see the ground through its orange haze, yet pressure, composition, and temperature profiles showed a world with weather and chemistry that echoed conditions thought to exist on early Earth. Farther out, Uranus and Neptune added more extremes. Miranda, a small moon of Uranus, displayed deep scarps, bright patches, and grooved terrain, as if pieces with different histories had been pressed together. The drop at Verona Rupes reached many kilometers, an unexpected feature on such a small body. Neptune's largest moon, Triton, orbited backward relative to the planet's spin, a strong clue of capture. Voyager 2 saw nitrogen geysers rising above its surface and thin streaks laid down by winds, evidence that even in deep cold, internal heat and seasonal sunlight could drive activity. The planets themselves were not simple disks. Jupiter's atmosphere broke into belts, zones, eddies, and long jet streams. The Great Red Spot became a resolved vortex with filaments and embedded swirls, one structure among many rather than a lone curiosity. Saturn's bands and storms were subtler but present, organized by rapid rotation and layered clouds of ammonia, ice high and other condensates deeper down. Uranus looked muted in visible light during the season of the flyby, yet processed images showed winds and faint bands. Neptune showed high contrast features, including the Great Dark Spot and bright methane ice clouds that raced along with very fast winds. Ring systems expanded from one example to 4. Saturn's rings broke into thousands of narrow ringlets, sculpted by resonances and by the pulls of small shepherd moons. The Cassini division held fine strands rather than empty space, and the Encke gap appeared as a clean corridor within the A ring. Transient spokes, radial markings that drifted across the B ring suggested charged dust interacting with the magnetic environment. Jupiter's rings proved faint and dusty. Uranus's rings were thin, dark, and sharply edged. Neptune's rings showed arcs, clumps that persisted in certain longitudes, likely confined by nearby moons. Rings went from exception to pattern. Wherever small particles are supplied and guided by gravity, disks can form and evolve. Magnetic fields added a different kind of map. Jupiter's field was large and strong, shaping a vast magnetosphere with radiation belts powerful enough to threaten electronics. Particles trapped in the field formed a torus along Io's orbit, supplied by volcanic gases that became ionized. Saturn's field aligned closely with its rotation axis, creating a cleaner, more symmetric magnetosphere that still produced auroras and radio emissions. Uranus and Neptune broke the alignment rule. Each had a magnetic dipole tilted far from the spin axis and offset from the center, making magnetospheres that changed shape over a planetary day. These findings widened the range of dynamos considered possible in planetary interiors. Spectrometers and radiometers provided the chemistry and thermal structure to go with the images. Hydrogen and helium dominated the giant atmospheres, with methane adding color at Uranus and Neptune by absorbing red light. Temperature profiles, derived from infrared spectra and radio occultations, set cloud heights and helped estimate wind speeds when combined with time-lapse imaging. gravity data from tracking refined masses, and hinted at internal density structures. Plasma and wave instruments mapped how the solar wind pushed against each magnetosphere and where bow shocks and current sheets formed. The number of known moons grew quickly. Voyager found new small satellites at every giant planet. Those bodies were not just add-ons. They shaped ring edges, fed dust to faint rings, and offered snapshots of how ice-rich objects evolve under different levels of heat and stress. Catalogs updated counts, but the deeper change was qualitative. Each moon had traits that pointed to a distinct story, some dominated by impacts, others by tectonics in ice, others by cryovolcanism or resurfacing. All of this came from a design that favored robustness and clear goals over complexity. Cameras and spectrometers rode a movable scan platform. Magnetometers sat at the end of a long boom to reduce interference. Particle detectors watched continuously. Operations worked around long, light time delays with preloaded command sequences and fault protection. The architecture did not rely on rapid updates. It relied on careful planning and calibration. Tape recorders stored data when the downlink could not keep up. The high-gain antenna returned the stream when geometry allowed. The scientific result was not a single headline, but a network of linked observations. Moons with tidal heating orbit, planets with strong fields and fast rotation. Rings respond to resonances with those moons. Magnetospheres pick up gas from volcanic sources and feed energy into auroras. Atmospheres that look bland at one season show structure at another. The outer solar system behaved less like a set of separate objects and more like a set of coupled systems. By early 1990, Voyager 1 had completed its close passes of Jupiter and Saturn and was moving outward past the orbit of Neptune's path from the vantage of the Sunday. The cameras were nearing retirement, but one more task remained: point back toward home and take a wide-angle mosaic of the solar system. The concept was straightforward and the execution precise. The spacecraft would rotate through a planned set of positions, take narrow and wide-angle frames of the Sun and the major planets, and send the data home for assembly. Engineers reviewed the risk. The cameras were not meant to stare anywhere near the Sun, even at long distance, and the optics could scatter light in ways that might mark a detector. By 1990, the risk was acceptable. The instruments had already met their main goals. The team built a sequence that limited exposure, kept the Sun mostly off-axis, and used short integrations where needed. On the 14th of February 1990, the plan ran. The result was a family portrait, 60 frames covering more than 30 degrees of sky. Most frames showed darkness with a few stars. In the fields where planets fell, small points appeared, each identified by geometry and brightness. Earth was less than a pixel wide in a narrow-angle image and happened to lie in a bright streak formed by sunlight scattered within the camera optics. The streak looked like a pale shaft, but the physics behind it was simple, stray light. The dot in that streak matched Earth's predicted position. The color of that dot reflected the same process that makes our sky blue when seen from the ground. Molecules in the atmosphere scatter shorter wavelengths more efficiently, and the integrated light from cloud tops and oceans adds to the effect. From billions of miles away, the net result is a small bluish signal when viewed with the right filters and exposure. The image did not show continents or clouds. It showed a single resolved pixel whose color and position identified it. The mosaic included frames of Neptune, Uranus, Saturn, Jupiter, and Venus. Mercury sat too close to the Sun to be imaged safely, and Mars was not favorable in that geometry. Labels added on the ground placed names next to faint points for context. The larger pattern resembled a sparse diagram drawn with real light rather than with ink, with the sun off to one side and the planets set by their true positions on that date. Once the data were received, image processors calibrated and combined the frames. They removed instrument artifacts where possible and kept the telltale streaks where removal would mislead. The final products were not made to impress with size. They were made to document positions and show scale. At the distance of Voyager 1, the sun fit as a saturated point rather than a disk. Planets were pinpricks. The empty space between them dominated. The mission then powered down the cameras. Optical imaging had high power and heating demands and was no longer needed for navigation or science at that distance. Other instruments continued to operate. Fields and particles sensors measured the solar wind, cosmic rays, and the changing environment near the edge of the heliosphere. The Deep Space Network kept the link by long, scheduled passes that balanced strength and antenna time. Discussion around the Earth image focused on perspective rather than technical detail. The frame placed our planet within a very large context, and it did so with no embellishment. A small blue point set in darkness is a simple statement. It carries no borders, no labels, and no foreground. The scale forces the viewer to think in units larger than a map or a globe. That was the reason for taking the picture. To document, with the same instrument that had mapped other worlds, the appearance of our own world from far away. The portrait also fixed a moment in time for later reference. Positions of planets are known precisely, so the mosaic can always be tied to the 14th of February 1990. At that moment, the spacecraft sat billions of miles from Earth, beyond the orbits of the giant planets from the Sun's point of view, with round-trip light time measured in many hours. Commands went out in blocks. Telemetry returned at low rates. The careful cadence of deep space operations framed the entire sequence, from planning to downlink. In the years after, the data from the encounters continued to feed studies in atmospheric dynamics, ring physics, magnetospheric processes, and icy geology. The single portrait frame containing Earth became a recurring reference in talks and classrooms, but its technical place remained clear. One image among thousands, taken with the same cameras and handled with the same calibration steps as any other. Its content was modest in pixels and rich in meaning, because context did the work. What followed used the same steady approach that defined the earlier phases. The spacecraft kept its antenna pointed home, balanced power among instruments as the radioisotope generators slowly faded, and ran sequences that fit light time delay. With the cameras off, the remaining sensors continued to return numbers on fields, particles, and plasma waves as distance grew. The solar wind builds a bubble around the sunday. That bubble, the heliosphere, is made of fast, thin plasma and magnetic fields streaming outward in all directions. Inside it, the sun's particles dominate. Outside it, the gas between stars, the interstellar medium, sets the rules. The boundary between the two is the heliopause. It is not a wall. It is a region where the pressure of the solar wind balances the pressure of the medium outside. Its shape shifts with the solar cycle and local conditions, and there is no visual sign that marks it. A spacecraft knows it by what its instruments feel: changes in particle counts, magnetic behavior, and plasma density. Voyager 1 reached that boundary first. For years leading up to 2012, its detectors saw a gradual drop in solar particles and a rise in galactic cosmic rays, the very fast particles that arrive from outside the heliosphere. Those opposite trends were an early clue that the spacecraft was running out of the sun's particle supply and entering a different environment. The magnetic field readings told a more complicated story. Models had suggested the field direction would swing sharply at the boundary. Instead, the direction shifted only a little, while the strength changed in ways that did not fit simple expectations. The mixed signals drove careful checks of every instrument and every assumption. A natural test arrived when a coronal mass ejection, an expanding shock from a solar outburst in March 2012, propagated outward and eventually reached Voyager's location in 2013. As that shock passed, the plasma around the spacecraft rang, producing oscillations that the plasma wave instrument could measure. The frequency of those oscillations depends on electron density. The measured value jumped by roughly a factor of 40 compared with the heliospheric interior, matching densities expected for the local interstellar medium. That density confirmation, together with the long-running particle trends, established that Voyager 1 had crossed the heliopause and entered interstellar space. Crossing the heliopause did not mean leaving the sun's gravity. The sun's pull extends far beyond the planets, past the Kuiper belt and into the distant Oort cloud, a vast, sparse reservoir of icy bodies that likely begins thousands of astronomical units from the sunday. A craft can move through interstellar plasma and still be bound, in a weak sense, to the sun's gravity. At Voyager 1's speed, the inner edge of the Oort cloud lies centuries away, and the far edge tens of millennia beyond that. The boundary that mattered for the instruments was not gravitational, it was the change from solar wind plasma to interstellar plasma. Voyager 2 followed a different path and crossed the heliopause in November 2018. Its instruments were in a different configuration, and it sampled a different part of the boundary. The particle change's magnetic behavior and plasma density jump provided an independent set of evidence. With 2 crossings from 2 directions and 6 years apart, comparisons became possible. The data showed that the heliopause is not a smooth sphere. It ripples and shifts with solar activity and local pressure differences, and the thickness of the transition region varies with time and position. Inside the heliosphere, the solar wind is hot but tenuous. Outside, the interstellar medium is colder but denser. The magnetic field outside is set by the galaxy and local interstellar clouds. Inside, it is wound by the sun's rotation and by the outward flow. Voyager's instruments, magnetometers, cosmic ray detectors, and plasma wave sensors can parse those differences. Particle detectors count high-energy protons and heavier nuclei from the galaxy, and lower-energy particles from the Sunday magnetometers record the strength and direction of the field. The plasma wave instrument senses density indirectly through natural oscillations. None of these require cameras, which is why both spacecraft could keep doing this work long after imaging shut down. Distance makes routine operations deliberate. Round-trip light time grows to many hours, so commands are bundled and sent in blocks, with built-in checks to handle delays and weak signals. The Deep Space Network, large radio antennas in California, Spain, and Australia, collects the returning data. By the time a Voyager signal reaches Earth, it is billions of times weaker than household electronics. Receivers integrate over long intervals and use precise frequency standards to pull the carrier out of noise. Sometimes multiple dishes are used together to improve sensitivity. Power is the hard constraint. Each Voyager carries 3 radioisotope thermoelectric generators, RTGs, that convert heat from the decay of plutonium-238 into electricity. The thermal power declines predictably over time, and the electrical conversion is steady, but limited. At launch, total electrical power was on the order of a few hundred watts. Decades later, it is a fraction of that. Operators have turned off non-essential systems and some instrument heaters to keep core functions alive. Instruments take turns when needed. The transmitter runs at lower power when link margins allow. The attitude control system uses thrusters sparingly to save propellant and power. Even with careful management, parts age. Tape recorders that once buffered images during the fast hours of a flyby are no longer needed. Computer memory can develop faults. Sensors drift with temperature. The team responds by changing which heaters stay on, by reassigning data storage, and by updating sequences to avoid vulnerable regions of memory. When a subsystem sends unexpected status, fault protection points the high-gain antenna at Earth and waits. Controllers then analyze telemetry and craft a recovery plan. Each iteration takes time. Hours to send, hours to hear back, and sometimes several cycles to converge on a fix. Tracking and navigation continue even in the sparse environment outside the heliosphere. Doppler shifts in the radio signal measure line of sight speed. Ranging marks signal travel time. These measurements refine the trajectory and help predict where the spacecraft will be relative to the moving Earth when it is time to schedule DSN passes. The geometry of Earth's rotation and the spacecraft's sky position determines which ground antenna can see it and when. The interstellar measurements now trickle in as long-term trends and occasional changes when a solar shock reaches the boundary. Cosmic ray counts reveal how the heliosphere modulates the galaxy's particle population. Inside, the sun's magnetic activity suppresses some energies. Outside, the spectrum rises. Plasma densities measured by the wave instrument show that the medium is structured and that shocks carry information far from their source. Magnetic field readings map a direction that differs from the spiral pattern inside and trace how the boundary drapes around the heliosphere. These datasets have practical uses. They constrain how the heliosphere shields the planets from galactic radiation, which matters for long-duration missions closer to home. They test models of how stellar winds carve bubbles in the interstellar medium, relevant to other stars and exoplanet environments. They also tie local observations to galactic-scale processes, since magnetic fields and cosmic rays carry energy over long distances. The spacecraft themselves record an engineering history. The high-gain antenna remains the most visible element, a white dish that must stay pointed within tight angles to keep the downlink strong. The long magnetometer boom still isolates the sensors from the spacecraft's own fields. The scan platform that once moved cameras and spectrometers is idle, but its alignment frame remains part of the pointing solution. The bus holds electronics behind thermal blankets that now do more work with fewer heaters. The RTGs continue to produce both electricity and waste heat, which operators balance to keep components within allowed temperatures. Failures and fixes accumulate as detailed notes. A memory location that no longer holds a bit reliably is avoided. A heater and its wiring that drew too much current stays off while temperature limits are adjusted elsewhere. An aging thruster is used less often. A single-bit error in a timing table is corrected with a small patch uploaded in segments and verified after each block. Each step is documented so that the next team, years later, can understand why a limit is set the way it is. Two lines of travel diverge across the sky. Voyager 1 heads in a direction that took it above the plane of the planets after its Saturn-Titan encounter. Voyager 2 remains in a different direction after Neptune. Neither path aims at a specific target. The next close stellar pass will be distant and far in the future. The spacecraft are small, dark, and unpowered except for their RTGs. They will not be visible as they move. Their radio transmitters, while they have power, remain the only connection. Crossing the heliopause clarified one more point about boundaries. There is no single agreed marker of leaving the solar system. Some people use the heliopause because it separates solar wind from interstellar plasma. Others argue for the Sun's Hill sphere, which marks the zone where solar gravity wins over galactic tides. Others refer to the Oort cloud as the last population of bodies that belong to the Sunday. Voyager's role is to report what it measures: particle counts, field vectors, and plasma densities. Labels can follow the physics rather than lead it. The cadence of work at Earth matches the distances involved. Schedules for the DSN allocate antenna time years in advance. Software and procedures evolve slowly. Training pairs experienced team members with new ones so that knowledge persists beyond any single career. Communications, discipline stays strict. Commands are checked by multiple eyes and simulations before transmission, because a simple mistake can be hard to undo when round-trip light time is measured in day-long chunks. Numbers fix the scale. Voyager 1 travels more than 17 kilometers each second relative to the Sunday power. At that speed, light still outruns it by a factor of about 10,000. One-way light time stretches to many hours. Two-way to nearly a day when geometry is unfavorable. The data rate from that distance is measured in bits per second, not megabits. Integrations are long and margins small. A weather front passing over a ground antenna can affect signal to noise. Operations account for that, with repeat passes and careful allocation of the best receivers. The interstellar medium that the spacecraft sample is not empty. It contains neutral atoms that drift through the heliosphere, ions that tie to magnetic fields, and dust grains that travel on slow, long paths. All of these can be measured indirectly, even when an individual instrument lacks a direct sensor. For example, cosmic ray modulation reveals magnetic turbulence levels. Plasma wave tones reveal electron densities. Slight changes in signal phase can reveal refractive effects from plasma irregularities along the line of sight. Power decisions continue as the RTGs fade. Heaters for certain instruments may stay off, accepting lower temperatures in exchange for keeping a detector alive. Voltage rails are monitored for stability when loads change. The transmitter's power amplifier is run at settings that balance reliability and link margin. Each instrument has a minimum duty cycle to collect enough data to see long-term trends, and teams negotiate trade-offs when two instruments compete for the same narrow power budget. Voyager 2 carries a different context because of its crossing date and path. Its heliopause measurements arrived in a different phase of the solar cycle. That allowed direct comparison of boundary thickness, local magnetic direction, and the sharpness of particle gradients under different external pressures. Differences are expected. The value is in measuring how large those differences are and how they correlate with solar activity that can be tracked near Earth. Glitches do not obey schedules. A single event upset can flip a bit in memory. A component can drift out of spec with age. When a subsystem misbehaves, the spacecraft's fault protection puts it into a safe configuration that points the antenna at Earth and waits. Engineers parse downlinked logs for anomalies, simulate the condition on the ground, and design a recovery. The fix may be a small change to a table, a power cycle for a module, or a change to the order of steps in a sequence to avoid a coupling that causes trouble at a certain temperature. Each action is conservative by design. The heliopause crossing matters for context beyond one mission. It gives a direct measurement of how a star's wind meets the interstellar medium. Other stars with winds will carve their own bubbles, large or small depending on wind strength and local conditions. Exoplanets living inside those bubbles will see particle and field environments shaped by those boundaries. The Sun provides the one case we can measure in situ. Voyager supplies the numbers that anchor models. The long cruise continues with a simple loop. Point the dish, run the sequence, collect data, and send it back. The spacecraft's time base keeps sequences synchronized despite temperature changes and aging. The DSN schedules track visibility and weather. Data are archived in formats that future researchers can read. Plots update slowly as new bits arrive. The scientific literature accumulates analyses that fold Voyager's in situ measurements into wider pictures of space environments. Golden records ride on the sides of the spacecraft, bolted beneath protective covers with diagrams etched into metal. They do not affect operations. They do not transmit. They exist as artifacts attached to machines that measure fields and particles. If the spacecraft passed near another star in a very distant future, the records will still be there, readable by any toolmaker who understands time, frequency, and geometry. Spacecraft do not last forever as active transmitters. Power margins shrink to zero. A final command may be sent to place a system in a stable passive state. After that, the objects remain in space, moving on trajectories set by gravity and the small changes imparted by past maneuvers. The data on Earth remain. Tables of particle counts, field directions in nanoteslas, plasma densities in electrons per cubic centimeter, timestamps in coordinated universal time, antenna logs with signal-to-noise ratios by minute. All of it traces a path from inside the Sun's wind to the medium between stars. The scale of that path is large in kilometers and modest in human terms. A small platform crossed a boundary that had been theorized for decades and reported numbers that matched a denser, colder plasma outside the Sun's bubble. A second platform crossed elsewhere and found the same broad pattern with local differences. The instruments that survived continued to count and to listen. Commands still travel for long hours across empty space, and responses return as weak carriers that receivers can lock and decode. Power on the Voyagers declines a little every year. Their electricity comes from radioisotope thermoelectric generators, RTGs that turn the heat of decaying plutonium-238 into current. RTGs are steady and simple, perfect for places where sunlight is weak, but the heat source fades on a predictable curve. At launch, the electrical output of each spacecraft was on the order of a few hundred watts. Decades later, it is less than half that, and the slope continues downward. What was once enough to run heaters, instruments, computers, and a strong transmitter now forces choices. Those choices follow a clear rule: keep the spacecraft pointed, keep the transmitter on, and keep at least some science instruments working. Everything else competes for the remaining watts. Heaters are the first lever. The bus is wrapped in insulating blankets, and waste heat from the RTGs helps, but individual components still prefer certain temperatures. As power tightens, teams shut off select heaters and accept colder operations for parts that can tolerate it. Next come instruments. Some require little power and can run almost continuously. Others draw more and move to duty cycles on for a while, off for a while, so the average load stays within the budget. Turning off an instrument is not an admission of failure. It is a planned step in a long sequence that began years ago. Priority goes to sensors that tell us about the environment outside the heliosphere. Magnetometers, cosmic ray detectors, and plasma wave instruments that infer electron density from natural radio tones. Cameras ended their work long ago. The imaging system was both power-hungry and no longer needed in darkness without flybys. Fields and particles instruments consume less and return slow, valuable data that map the interstellar medium. The transmitter is the last thing anyone wants to touch. It is the only voice the spacecraft has. As power drops, operators trim around it, lowering transmitter power when link margins allow, scheduling longer deep space network passes and packing bits efficiently. The DSN's large antennas in California, Spain, and Australia listen for a signal that arrives billions of times weaker than familiar electronics. Receivers integrate for long stretches and lock onto the carrier with atomic clock stability. When weather or maintenance takes an antenna offline, schedules shift to other stations. If geometry limits the view to a single site, mission work pauses and resumes with the next visibility window. Care extends to software and memory. Voltages and temperatures drifting out of their original ranges can reveal weak spots. A single memory cell that fails to hold a bit reliably becomes a region to avoid. Engineers remap tables, split code across locations, and adjust sequences so that critical values live in the healthiest memory. Updates travel in small blocks, each verified before the next is sent. Round-trip light time tens of hours forces patience. A bad uplink can be retried, but every retry costs days, so reviews are strict and simulations thorough. Glitches happen. A radiation hit can flip a bit. A component aged by cold and time can misbehave. Fault protection stands between a glitch and a lost spacecraft. If limits are crossed low voltage, bad attitude, loss of lock, the system points the high-gain antenna to Earth, quiets non-essential loads, and waits. Controllers then read back logs, compare with ground tests, and craft a recovery plan. Sometimes the fix is a power cycle for a module. Sometimes it is a tiny change to a timing table. The risk profile is conservative. The aim is to restore function without triggering new faults. The RTG's declining heat sets another constraint: thermal balance. Without certain heaters, components operate colder than their original specification. Lubricants stiffen, oscillators drift. Voltage regulators respond differently. Operators track these effects and adjust margins. In a few cases, unused pathways, voltage regulators or power lines designed for contingencies have been brought into service to reclaim a small fraction of a watt or to route power more directly, buying time for a sensor or a heater. Small gains matter when the budget is measured in single digits. Even with less power, the remaining instruments still report on a place we have never sampled before. Cosmic ray detectors measure high-energy particles arriving from the galaxy. Their counts rise and fall with solar activity as the heliosphere expands and contracts, modulating which energies can penetrate to the spacecraft. Plasma wave sensors hear the medium ring when distant solar shocks pass, and from the pitch of that ringing derive electron densities. Magnetometers trace a field direction that differs from the spiral pattern inside the heliosphere. Together, these numbers describe the edge conditions of our star's bubble and the properties of the local interstellar cloud. Communications discipline mirrors the distances. Commands are prepared in blocks, checked, and transmitted during scheduled DSN time. Telemetry returns as frames at very low data rates. Weather on Earth can change the noise floor. Schedules include margins or repeats to secure critical data. A repair outage at a southern hemisphere antenna has, in the past, paused commanding to one spacecraft until the dish returned to service. When it did, contact resumed and planned tests continued. Events like that are built into planning. The long view includes kinematics. The spacecraft will not approach another star soon. A nearest pass, within a couple of light years, lies tens of thousands of years ahead for one trajectory. The other path has no close target within comparable time. They are unpowered, except for their RTGs, which will eventually no longer run radios. Their masses are small and cross-sections tiny. Collisions are unlikely. They will pass between stars silently, while the records of their operating years sit in archives on Earth. The golden records mounted on each spacecraft remain attached to the bus. Their covers carry instructions arranged to be readable by any toolmaker who understands frequency, time, and geometry. Etchings show the hyperfine transition of hydrogen as a time unit, a map of pulsars with their periods as a location finder, and a diagram for reproducing audio and pictures from an analog groove. If a finder ever removes the cover and plays the disc, the sequence begins with greetings in 55 human languages. Then, the natural sounds of wind, surf, thunder, and animals, and then a program of music that spans continents and centuries. The audio portion ends with instructions for decoding 116 images recorded as a modulated signal, which include pictures of landscapes, plants, animals, human anatomy, everyday scenes, and scientific diagrams. Interpreting that content does not require shared culture. It requires pattern recognition and physics. A listener who recognizes harmonics can identify pitch and scale relationships in the music. A viewer who follows the timing marks can reconstruct images line by line. A reader of the cover can convert the pulsar map into a location if they know pulsar timing. The messages do not assume a spoken language. They encode ratio, rhythm, and geometry. That design is the simplest way to send a durable, self-describing artifact without a shared standard. Speculation about a future finder is a thought exercise, not a mission goal. The spacecraft do not broadcast their position for others to hear after their radios are off. Any discovery would come from chance interception and careful inspection. The hardware itself tells a story even without the disk. The high-gain antenna, the magnetometer boom, the scan platform, and the RTGs describe a machine built to sense, to point, and to communicate. Markings on the structure show unit conventions and tolerances. Materials reveal vacuum-stable coatings and thermal design for a weak sun environment. The human work continues while the instruments run. Teams at the Jet Propulsion Laboratory schedule DSN time, monitor telemetry, and maintain long-lived software in environments that have outlasted generations of computing hardware. Documentation links decisions made decades ago to procedures in use today. Training pairs experienced staff with those who will carry the last years of operations. The cadence is slow. Plan, review, send, wait, assess, adjust. The patience that governed flyby sequences now governs interstellar cruise. Public attention rises and falls with news cycles, but the data stream is steady. Papers analyze long-term trends in cosmic rays and plasma density. Models of the heliosphere use the measured boundary conditions to improve how shocks and fields propagate. Comparisons between the two crossings show that the heliopore's thickness and shape change with solar activity and local conditions. The conclusion is not a single number. It is a range that responds to time and direction. At some point, the power budget will no longer sustain even a minimal set of sensors and a transmitter. Before that, instruments will be shut down in a planned order to free watts for items that must remain. After that, an end-of-mission sequence may place the spacecraft in a passive, thermally stable state. Once the transmitter is off, there will be no way to know the internal condition. The objects will remain on their trajectories, with attitude drifting slowly as thermal radiation and minute torques act over long times. The paths after planetary flybys determined where each vehicle now heads. Voyager 1's turn near Titan, centered above the ecliptic, toward a high latitude relative to the Sun's equator. Voyager 2's path stayed closer to the planetary plane and then diverged after Neptune. Neither path returns inward. Each is a one-way outward arc set by gravity and a series of precise aim points chosen decades ago. The engineering record is useful on its own. It shows how to run a mission for decades with shrinking margins. It shows how to make conservative changes to code in memory that can never be touched physically again. It shows how to plan operations around light-time delay. It shows how to value simple, well-characterized hardware over complexity when maintenance is impossible. These lessons carry into other long missions that will face similar constraints far from the Sunday. The cultural record is accessible without launch or antenna time. Sounds of wind and surf, greetings in many languages, images of people and landscapes, these are public and can be studied, argued over, and reinterpreted. Their selection reflects limits of time and budget, and the tastes and knowledge of a small group at a specific moment. The artifact is not a census, it is a compact sample. Its value lies in being understandable by readers who begin with physics rather than with a shared language. Much of what the spacecraft encounter now is invisible to human eyes. Densities expressed as electrons per cubic centimeter, magnetic fields in nanoteslas, particle fluxes by energy and charge, radio tones at kilohertz frequencies. The maps that result are simple lines and numbers. They tie the Sun's influence to the galaxy's medium through data rather than metaphor. The files that hold them are small in modern terms and large in importance because they come from a place no other instrument has reached. Future flybys of stars are calculations, not plans. A fraction of a parsec from a dim red star tens of millennia from now is a number derived from current trajectories. No one will guide those encounters. Gravity alone will. The spacecraft will not slow. They will not aim cameras that no longer work. They will not transmit. They will carry metal covers with etched diagrams and discs that can be played by a finder with patience. Closer to home, antennas on Earth continue to turn. Schedules fill with hours reserved for faint signals at the edge of the DSN's reach. Software that once processed planetary mosaics now passes low-rate telemetry from a plasma wave detector. Spreadsheets track power budgets in tenths of a watt. Logs mark each command, each response frame, each unexpected reset. The rhythm remains the same. As the distance grows, point, measure, encode, transmit, receive, decode, archive. The record of the mission runs in two threads: the science of a boundary between a star's wind and interstellar space, and the practice of operating hardware far beyond its original timeline. Both threads continue as long as power and links make it possible. For years, Mars drew most of the attention. Voyager widened the field. It showed that many places, not only planets, could matter for chemistry, weather, and even the basic conditions life might need. Moons once thought to be frozen leftovers turned out to be active. Atmospheres were stranger than models had assumed. Weather ran faster, deeper, and longer than anyone had seen from Earth. That shift carried forward. Later missions did not repeat Voyager. They refined it. Galileo took up the Jupiter thread. It entered orbit, sent a probe into the atmosphere and used long campaigns to turn snapshots into time series. The mission mapped jets and waves, measured lightning, and followed how energy moved from equator to pole. Europa's fractured ice, first made clear by Voyager, became a target for systematic study. Galileo's magnetometer detected signals consistent with a conducting layer under Europa's shell, evidence that fit the ocean idea. Io's volcanism, dramatic in Voyager frames, became a laboratory for tides, heat flow, and plume chemistry. Cassini extended the Saturn work, Voyager's ring structure, and the hints of activity on several moons set the questions. Cassini answered with years of orbits, radio occultations through the rings, and repeated flybys. It imaged ring waves launched by resonances and watched ring edges respond to tiny moons. It found jets at Enceladus and traced their material into a donut of gas and dust around Saturn. The Huygens probe, released from Cassini, dropped through Titan's thick atmosphere to a cold, dark surface with pebbles rounded by flow. Titan's chemistry, which Voyager had outlined in bulk, became a detailed map of methane clouds, rain, and lakes. Juno returned to Jupiter with a different aim. It flew close over the poles on a high-inclination path and used microwave radiometers and gravity science to probe deep flows. Where Voyager had shown cloud belts and the Great Red Spot in visible light, Juno measured how far down those structures reach and how the magnetic field is built. The mission found fine-scale patches and bands in the field, signs of a complex dynamo in a conducting interior. It mapped auroras, where particles follow field lines into the atmosphere. The work spoke to the same physics Voyager opened, but with new tools. New Horizons carried the flyby model outward. It crossed the Pluto system and, in a single fast pass, turned a distant dot into a layered world with glaciers of nitrogen ice, a thin atmosphere, and mountains of water ice. The planning, imaging, and data return followed the Voyager pattern. Long cruise, a dense command sequence at closest approach, and months of downlink. The mission used Jupiter for a gravity assist, an idea proven at scale by the Grand Tour. These steps were possible because Voyager changed expectations about mission length. A craft could survive far from the sun for many years if the design was straightforward, the power steady, and operations disciplined. That lesson influenced how agencies funded multi-decade work and how teams trained people to hand off knowledge. Students who joined during the flybys became the mentors for later phases. Procedures, checklists, and power budgets turned into living documents rather than one-time plans. The cultural track followed alongside the science. Voyager appeared in films, books, and classrooms, not as a spectacle, but as a steady presence. The Golden Record, built quickly and added with little mass, became a familiar symbol. Museums showed replicas. Musicians sampled its audio. Writers used it to anchor stories about contact and memory. The idea that a small object carries a self-explaining message, audio, images, and a map proved strong enough to last beyond the news cycle. It is easy to misunderstand that symbol as decoration. It was designed to be read by anyone who begins with physics. Engineering circles still point to the hardware choices. The high-gain antenna, fixed and simple, trades flexibility for reliability. The magnetometer boom moves sensors away from interference rather than fighting noise with complex electronics. The instrument suite uses narrow power bands and clear sequencing. Tape recorders, now retired, buffered data when downlink could not keep up. The computer is small by modern standards, but uses table-driven logic that can be updated with tiny, verified patches. This style is not fashionable, but it works when maintenance is impossible. Voyager also moved some questions from theory to measurement. The shape of a giant planet's magnetic field, the way the solar wind meets the interstellar medium, the thickness of a ring, the speed of winds on a distant blue planet, these now have numbers attached to them. Models still matter. They are sharper because they are anchored in data. The same is true for the heliopause. It is not a clean edge. It moves, thickens, and thins with the solar cycle. The jump in plasma density that marked Voyager 1's crossing in 2012 and Voyager 2's crossing in 2018 set scales for the local interstellar medium and for how our star's bubble compares with others. The mission team continues to work at a slower cadence. Power fades in small steps. Instruments take turns. Heaters are off in some zones that were once kept warm. The transmitter remains the priority because it is the only link. Commands go out in blocks. Telemetry comes back at low rates and is archived in formats chosen to be readable decades from now. When a fault occurs, the craft points the dish at Earth and waits. Engineers read the logs, simulate the condition, and send a careful fix. The rhythm is patient by necessity. What the spacecraft measure now is not dramatic to the eye. It is counts of particles by energy and charge, magnetic field strength and direction in nanoteslas, and the pitch of plasma oscillations that reveal electron density. Trends stretch over months and years. A shock launched by the sun takes a year or more to reach the boundary and ring the local plasma. Cosmic ray counts shift with the sun's activity level. The field direction outside differs from the spiral pattern inside, and it drapes around the heliosphere. Each piece adds to a picture that will be used by missions that follow. The golden records remain bolted to the buses. They are not part of flight operations. They need no power and make no demands. They exist within the larger frame of a mission that values traceability. Every diagram on the cover ties back to units, constants, and timing that are common to any toolmaker. If a finder reads the pulsar map, playback guide, and units, the rest unfolds. Greetings in many languages, natural sounds, music that spans styles and centuries, and images that map biology, geography, and daily life. That package does not claim to be complete. It claims to be understandable. Voyager's influence shows up in less visible places. Mission proposals now assume long duty cycles and slow returns from distant targets. The Deep Space Network plans for faint carriers that need hours of integration. Software and documentation are written for teams who will inherit rather than originate. Training includes how to change little and test much. These habits are responses to the reality of distance and time. The arc that began at Jupiter and Saturn now reaches into interstellar space. The craft report on a medium that flows around stars and carries fields and particles over vast ranges. They are not heading toward a chosen star. They are moving along paths set by gravity and by the aim points chosen long ago. The next close pass near another star, if it happens at all, lies tens of thousands of years ahead. The transmitters will be off long before then. What remains on Earth will be the record, tables of numbers, plots of trends, and notes on how each decision kept the link alive a little longer. There is also the quieter legacy, how people talk about exploration. Voyager suggests that patience is not the same as delay. A slow stream of bits can change what we know if it is steady and well understood. A clear question can survive the long wait for an answer. An instrument that measures one thing well can be more useful than a complex device that measures many things poorly in a harsh environment. These are not slogans. They are practices that show up in the way teams plan and operate. At some point, the last instrument that still returns useful data will be switched off. The transmitter will follow. No alarm will sound. Antennas will listen until schedules move on to other work. The final frames of telemetry will join the rest in an archive. After that, the craft will keep their courses. The RTGs will cool. The metal will hold together in cold vacuum. The records will ride on, sheltered under their covers. The sky does not change because a signal ends. The heliosphere still meets the interstellar medium. Other stars still carve bubbles of their own. Other missions will use the numbers returned from the edge to build their plans. A person can open a dataset, run a script, and see the curve of a particle count rise and fall with solar activity. A teacher can show a small blue point in a beam of scattered light taken from far away and explain why molecules scatter blue more than red. A student can read a diagram etched into a golden cover and understand the unit of time chosen and the reason for the pulsar map. 2 small spacecraft, built with 1,970 seconds methods, made those moments possible. They did it with steady pointing, careful sequencing, and a transmitter that has worked longer than anyone expected. They relied on clear decisions: what to power, what to measure, when to send, and how to protect the link. They did not ask for attention. They asked for calibration and patience. If you step back from the details, a simpler picture appears. We learned how a great storm moves on Jupiter and how a ring holds together at Saturn. We learned that ice shells can hide oceans, that small moons can stay active, and that blue planets at the edge of sunlight have fast winds and tilted fields. We learned that the sun's wind forms a bubble, that the boundary is structured, and that the medium outside is denser than the plasma within. We learned that a record can be built to explain itself to a stranger who begins with physics. None of these lessons are loud. All of them endure. Some distance ahead, the data rate will drop to 0. The antennas on Earth will point elsewhere. The path of each spacecraft will carry on in dark space where atoms drift far apart and time is measured in long, even steps. The objects will be quiet, but their work will remain in the files that people open, study, and teach. The questions they raised will continue in other designs and other plans. Out past the planets and the reach of the solar wind, 2 machines keep steady attitudes and slow rotations. Their heaters cycle less often. Their instruments take turns. Their radios send at rates that would seem small to anyone used to a fast link. And yet the signal lands, is decoded, and adds a point to a plot that grows by one more dot. It is not a spectacle. It is a long line drawn with care. Some endings are sharp. This one will be gentle. As power slips and instruments rest, the link will thin to a final thread and then to quiet. The numbers already sent will keep their meaning. The diagrams on 2 golden covers will keep their instructions. The paths will keep going simple arcs through a wide, cold place, while lights here dim for the night and come on again in the morning, and the habit of listening, learned over years, softens into a calm, open silence.